There we go. Okay, here we are once again. This is Physics 105A, video lecture 10. And we have a guest today. But more about that later. Okay, let's start with some announcements. The exam has been graded and it went fairly well, so there's nothing to worry about. I will return the scores to you guys within a day or so, or actually possibly by the time you get this video, the scores will be there. And so as always, the new homework is the rework of the exam. And that will be due on the coming Friday, whatever that day is. And I'm going to just discuss the problems one by one that were on the exam, and we'll add a little bit to them, and I'll show you how great they really are. Okay, so you guys can enjoy reworking those problems, and let's get started with that. And I'm just going to sketch the discussion of the problems. You have them in front of you, of course, and you've tried them out already. So for the first problem, the reason I drew that graph, I had actually intended to have you guys sketch the graph, but I just wanted to avoid complications. So I gave you that graph, and the Fourier coefficients of that we had already done in class in terms of the Fourier transform. Formally, it's the same thing in this particular case. Now, so we needed the C sub k 1 over 2 pi minus pi pi of x e to the minus I k x dx. Okay, we needed that integration. And what happened to a number of people was they integrated over the entire interval, but this function was defined to, vanish outside plus minus a. So we really had to integrate minus a to a, 1 over a. And once you make sure you do that, and you know some definitions of Euler's formula, you'll get the sine kx over ak, or sine ak over ak. And you'll end up with the, if you interpret it as a function, you get this thing here. And there's a reason it reminds you of the single slit diffraction, okay? Very closely related there. Okay, so that one, if you didn't get it 100%, you're going to want to redo it. Oh, actually, that's what I was going to say. If you didn't get 25 out of 25 on any particular problem, then you just want to include it in your rework. Okay? If you got 25 out of 25, then don't bother. So that's problem one, right? Very interesting. If you'll look it up in your notes, you'll see we've actually already done it before. Problem two is also interesting. We had, again, we wanted the Fourier coefficients of a function. This one here, I'll put it in a box. Okay. So we've got that absolute value of x, and of course, no one likes to deal with absolute values. Alpha is positive. So I went ahead and included a graph of this, and since we're working with this again, the goal is to get this 48 coefficient. I'll just leave that formula up and discuss the graph. So here we go. Pi minus pi. This must be 1, and it's exponentially decreasing. It's a symmetric function. So first of all, you're going to have to break this integral up into a left half and a right half. So if you continue this, it's going to be 1 over 2 pi minus pi to 0. And then what are you going to have? E to the alpha x for the left half. E to the minus pi kx dx. Okay, then you combine these, and it's really a trivial integration. And I'm going to go ahead and it's not the whole thing, plus, plus the other one, plus the right half. So because it's this basic exponential, you put these all alpha minus ik times x, and the integration is just done. You don't have to simplify the result much. Anybody have to do that? That one and the second one. Good, so then you have your c sub k here, your Fourier coefficient, and then I asked you guys to take some limits. But let's talk about the limits without even looking at the expression. Namely, when alpha goes to 0, this function is just equal to e to the 0 equal 1. So when alpha goes to 0, I'll go ahead and draw it like this. I'll draw it fat. We'll have this function here. And if the function's just a constant, it's the c sub 0 that must be equal to that constant equals 1. Everything else is going to have to vanish. So that's why limit alpha goes to 0 of c sub 0 has to be equal to 1. And it's something with an alpha in the denominator, so it's not trivial, but we've done limits like that before, so it's pretty standard. And that's also why the limit for all the other c sub k's has to be 0. They all have to just be 0 because the entire Fourier series just consists of that constant 0th term. Okay. So yeah, that's an interesting problem actually, and it's one that we can do. If you're interested, you can also look at it in the limit as alpha goes to infinity. Right? Alpha goes to infinity, you would just have this ever narrower function really consisting of one point there. But your Fourier series is going to tell you that everything vanishes, which is fine. Okay, good. So that was problem number 2. And yeah, you definitely want to take a good look at that again. A lot of people did some funny business here with the integration, and then it was all hopeless. Okay, let's look at the third problem. Let's look at the third problem. Okay. So there we were talking about the central force formalism, and I had given the force as, actually I gave, let's write the whole thing down. F R, so it has this form, okay, and the force that we were talking about was minus alpha over R. So that just contrived. One person interpreted this as 1 over r squared and did the whole r squared version of this. So they knew what they were doing, but they, were a little hasty there. Yeah, is this contrived or is this relevant? This is actually a really interesting example. So what has a 1 over r force law? It's not a point particle. You may remember from electricity and magnetism, a line charge, an infinite line charge. In a plane perpendicular to the line charge, we'll have a 1 over r force law. And charged particles going past straight wires, there's a whole industry for that. So this is a very relevant problem right here. Good. So that we had to get the potential energy, and that was just going to end up being the natural log r over a. Okay. And then we were going to draw the effective potential, and then your natural log goes up like this, and your L squared over 2m r squared goes down like that. So where the minimum is located isn't quite clear, because it depends on the value of alpha as to if it's above or below the axis, but that's neither here nor there. The generic or the basic form is like this, and it's growing logarithmically. That's also a formal problem in terms of bounded and unbounded states, but there's your effective potential. And you have to find the minimum of it by your first derivative criterion, and then you can just take it from there all the way to the end. So you find the minimum of it, then you know you're talking about circular orbits. And I then asked for omega sub r equals u effective second derivative r0 over m square root, straight out of the theory of one-dimensional oscillations. So we asked for that. And we're actually going to return to this in the coming discussion because we're headed towards a discussion of circular orbits and nearly circular orbits. So this will be a very good example to keep in mind. But yeah, that was the gist of the problem right there. First derivative criterion gets you the location of the minimum. Some people thought it was just this letter A here, but it was not. And the second derivative is net frequency of oscillations. And of course, if we're doing circular orbits, we can also talk about omega sub phi, which we get out of the angular momentum expression. So good. So that's problem 3. Do a quick discussion of problem 4. And on problem 4, I'm going to give a little extension to what was on the exam just to make it more interesting. So here we had a central force problem again, and I drew two masses connected by springs, by a spring, and I said in the exam, relaxed length A. So nobody took that into account. So if it's relaxed length A, that's where it's storing no energy. And the first thing we wanted to do, oh, and I also gave the hint about the reduced mass. So this is a central force problem. Central force problem, right? Just a Hooke's law between these two masses in space. Okay. So central force problem, therefore we have the whole formalism that we want to explore a little bit. So yeah, we've got the reduced mass, and people were seeing that too since I mentioned it. M1, M2, M1 plus M2. Okay. But the potential energy, I don't think anybody wrote this down. Remember, it's minus integral f of r dr. You know, this A isn't necessarily associated with this one. I'll just put this empty up there for now. Cut it down there. Okay. Like so. Okay. So what do we have here? We have minus, and then since we have a Hooke's law, we have minus again, K R minus A dr. Okay. So what we're going to get is 1/2 K R minus A squared. 1/2 K R minus A squared. And that's where I've just chosen, yeah. You guys figure that one out, right? This is the difference. So when R is equal to A, we have 0 here, fine. But that allows us to have compression and stretching, which is what we really need for this thing to oscillate. So just saying 1/2 KR squared wasn't quite right. Okay, so you've got this thing. Now let's go ahead and look at the effective potential. So the effective potential, not even just the effective potential, let's look at the energy. Okay, 1/2 m r dot squared plus L squared over 2m r squared plus 1/2 K R minus A quantity squared. There's the energy. Of course, this is the effective potential. So if we wanted to graph that, and now I'm going to start saying homework, because that wasn't on the exam, but if we wanted to graph this, what would we do? We could draw both of these r-axis. We know our good old L squared over 2m r squared like that. This one, if we look closely, we say, okay, here's a point A and we've got parabola. But then you could actually accuse me of introducing a fiction here. Because this parabola, if it has its minimum point here at A, it's going to extend in the negative r-axis, which of course in reality doesn't happen. In reality, this is a Hooke's law spring, fine, but if you press hard enough to it, you get to r equals 0. Before you get to r equals 0, it gets really hard to press. So that means that the true potential of this system, effective potential, is going to be limited to here, and it'll go up somehow like that. It won't be perfectly symmetric around A. Be that as it may, you guys are going to want to just draw this with that caveat. Okay. So there's your effective potential. And now we can actually ask about what this molecule would do if it's vibrating or rotating. Okay, so there's more going on than was asked for in the homework, in the exam problem. Now in the exam problem, I said, good, let angular momentum vanish, and then you just have 1/2 m, so L equals 0, you have plus 1/2 k r minus a squared equals e. So nobody did it this way. You didn't, strictly speaking, have to. Other people wrote down the central force. Okay, that was legitimate as well. But now we want to do it this way, because we should just be able to look at this and declare victory right here. Okay. Recognize this as a harmonic oscillator. If you make a substitution, just some other letter, z equal r minus a, where a is a constant, and then rewrite the energy in terms of that, you'll see it's just the energy expression for a harmonic oscillator. So omega squared is k over m, and m happens to be the reduced mass. Now, so good, so you've taken care of that in your rewrite. That's one way to have done the exam. The next thing is to look at the full case where rotation is possible. In other words, where L is not equal to 0. Then you'll find that the omega sub r that we're often looking for isn't so easy to find. So I'm going to say omega sub r squared is equal to u effective double prime at r0 over n. Because of the form of this thing, we can't actually get this explicitly. So instead, I'm going to say find a relation between omega sub r squared, or a relation that includes omega sub r squared and omega sub phi squared. So let me just write that down somewhere here. Put that up here. So what happens is if you start looking for the second derivative of u effective, and you find that you can't actually solve, find the r naught explicitly, there will be a relation. Find a relation with including or with omega sub r squared and omega sub phi squared. That's interesting in its own right. Okay. So even this is a very interesting central force, because like I said, it's a molecule basically. It's not, doesn't have a spring in between it, but it has an equilibrium distance, separation distance, and radial and rotational oscillatory modes. Okay, good. So that's enough for the exam. Anything else interesting you find about those problems, you can write down as well. So that'll be due on Friday, whatever that date is coming up. Okay, so now let's move into some new material. We're going to be spending a lot of time continuing discussing the central force problem, Kepler problem, and related things. So our next topic is circular orbits, and then, which there's not that much to say about those, but nearly circular orbits is a rich topic. So circular and nearly circular orbits. Circular and nearly circular orbits. Circular orbits, okay. So this is still just the central force problem, not strictly speaking the Kepler problem, just the general central force problem. Circular orbits are going to be at the minimum of an effective potential. So we're back again to writing down our effective potentials, which I'll do. So I'll just go straight to the energy expression again. Central force world 2mr squared U of r equals E. Here's the radial equation. Here's our effective potential. And I'll go ahead and draw our generic Kepler version, Newton version, just because it has a lot of the essential features. Okay, nicely exaggerated here. Our effective, clearly the circular orbit right here, r sub 0, and what I like to call E sub 0, energy corresponding to that circular orbit. Okay, well, as I just stated earlier and we've seen before, that's the minimum of the effective potential. So circular orbit here when U effective prime or equals 0, right? That's how we locate first derivative criterion. So let's go ahead and do this again. So we have U effective or U of R. We have to have a local minimum, by the way, for the orbit to be stable. But for now, well, we'll talk about that in a bit, but for now we're not even making any stipulations here. So anytime we can set this equal to 0, and that is minus L squared over mr cubed, because we have r to the minus 2, plus u prime of r equals 0, and so we can put our little r sub 0 in there by hand. Okay, that's the equation. And what does this mean? Well, good to hold on to the fact here, we can always make this substitution. So if we've got a u prime of r0, we can say it's equal to L squared over m1 cubed. Okay, that's a technique that often comes into play. Right now I'm going to remind us of what this L here means. Let me go ahead and erase this. Remember we have m r squared phi dot is equal to L. And L is the conserved angular momentum. So what I'm going to call omega sub phi, that's just phi dot of the circular orbit, because now it's a constant as well, so that's equal to L over m r naught squared. And using this thing here, we're going to have L squared over m r naught cubed m r naught, and what's r naught squared? Okay. R naught squared is equal to L over m omega sub phi. Okay. Actually, let's do this a little bit different. Let's do it this way. U prime R0 equal to L squared over R naught cubed. And just work straight off of this thing here. Okay. We'll put the L squared in there. So then we have m squared R naught to the fourth omega sub phi squared over m R naught cubed. That's what we're looking for. So here we have U prime R0 is equal to m R naught omega sub phi squared. Okay. This is nothing other than the centripetal force formula, right? The U prime is your force. It's a central force, so it's centripetal force. And the m r naught omega phi squared is, of course, the same as, I'll just put it in here, m v squared over r naught. So yeah, this thing is very important. This omega sub phi and its relation here to u naught phi. So yeah, we're talking about circular orbits, and that's the big punchline. And because this omega sub phi is constant, I'll just add as a note here that we'll use omega sub phi t sub phi is equal to 2 pi, okay, just by definition, right? So frequency period 2 pi. Okay, so that's circular orbits. Now we want to talk about nearly circular orbits, which is where it gets interesting. So I'll erase everything and then probably reproduce some of this stuff. Good. Those are circular orbits. Now the nearly circular orbits are of great practical importance. Our elliptical orbits of the Kepler problem, even the planets are often very close to circles. We have many circular, nearly circular, and elliptical orbits of artificially placed satellites in orbit around the Earth. So it's also a really practical matter of understanding these nearly circular orbits without integrating up full Kepler's law. Okay, let's have a look here. So the nearly circular orbits. And we'll start with a circle. Okay, imagine this is a perfect circle. There's the center of potential, center of attraction. And suppose we're riding in some kind of satellite, which is a dot with antenna on it. Okay, so we're riding in the satellite. And how can we perturb this orbit to make it non-circular and still maintain the value of the angular momentum? So we've got a circular orbit. It's So I'm going to go ahead and rewrite this out. Circular orbit with angular momentum L equals constant. Now you'll notice that whole formalism we've been using is always assuming that L equals constant. We want to keep L equal to a constant, but L is constant as long as there's no net external torque. So what we can do to change our orbit, perturb it a bit, is fire our rockets either towards or away from the center of that circle. There's no torque associated with that, but there is an addition of energy to the orbit now. Okay, we've released some energy, there's an addition of energy to the orbit, and that's going to turn this thing into what? Okay. What kind of a perturbed circle will that be? Well, it'll actually be an ellipse because it's just another part of the Kepler problem. But it'll be an ellipse that's very, very close to a circle. Good, so let's put that into words here on the board so it doesn't get lost. So I'll write perturb the orbit by exerting, okay, so your rocket or whatever you have, a radial force. Okay, so we fire blasters towards the center or away from the center. No torque. So this retains the constant angular momentum. And now you'll see how this is going to show up in our effective potential. Because basically speaking, here's our circle. Go ahead and draw an R sub 0 here. How about that? There we go. There's our circle, R sub 0. There's the corresponding energy. So that's E sub 0. Now I've exerted a radial force, and I've added energy. So now I have a little E0 plus delta E. So squeeze that in here. E0 plus delta E. Right? That's a little boost of energy. That's up to here. And of course the drawing is nice and exaggerated, but there is the new R0 plus delta, R0 minus delta R. So if that's my R0, then this is my R0 plus delta R. This is my R0 minus delta R. Okay. And so now I'm back in the full Kepler problem, but since we're close to R sub 0, the idea is it's just a small perturbation, perturbed. Since we're close to R sub 0, it's nearly circular orbit, and we can continue the analysis here on this graph. We don't have to go do that big giant integration again. Okay. So we've got the perturbed orbit. Since we're near a local minimum, so R0 is a local min, or a point, yeah, where E takes on the local minimal value. U effective. And then we're looking at that as a small oscillations problem, so we have omega sub R root U effective second derivative of R0 over M. Okay. So this problem now is an interesting problem. We've just got a little oscillation here. Okay. We're close enough to the minimum. We can write this down. A little more room here. Write this down as the volume. Now, we can say R of T is equal to R sub 0 plus a little delta R cos, encroaching on that picture. Let's try it again. Okay, so now RT equals R sub 0, that's just the circular orbital radius, plus this little delta R cos omega sub RT, and I'll ignore that there's an unknown phase in here, we don't care. Okay. And because these are ellipses, we know they're Kepler ellipses, if we're talking about the Kepler problem, then they would be, this would just be a shifted ellipse, okay, a shifted circle in a sense. But yeah, this would be an approximation to an ellipse. Now in general, if this is not the Kepler problem, then we have to find out what this is. What we have is a circular orbital motion, like this, where at the same time, here's your circular motion, at the same time this R is changing in T. For example, for the Kepler problem, it would go like this, and then it would go back to here. But in general, it's not going to be a closed orbit. In fact, the exam problem number 3 had exactly the situation where it's not a closed orbit, so we'll return to that as well. Okay, I want to get to the punchline on all this. So let's see here. Oh, the other thing we can say is we have an R min and an R max the way we did before as well. So the other way to look at that is draw these two circles is the way we've done it in the past. We have these two concentric circles. Now they're actually very close together, but our picture has them really separated. So what we're looking at is this counterclockwise motion, which would be the omega phi. So omega phi is the angular velocity, and it's a constant, but at the same time as this thing is sweeping out the counterclockwise circle, the radius is changing. So this is the R min, and you can imagine the R min increasing and reaching its R maximum right there. This is the crucial picture. Different colors would be nice, but we're not having them. Okay, so, and then this here would have swept out from R min to R max in what? Half the period of these oscillations. Okay. Let's go ahead and add down here where we have some room. Omega sub R, T sub R is also, of course, by definition of equal to 2 pi. So what I'm going to introduce now is a quantity here, namely this angle that we just saw swept out, C. That's the angle that's swept out between the minimum and the maximum radius. So as omega sub phi, just go in here counterclockwise, this oscillation here, this back and forth oscillation, has its own period, and we're combining these two. So having introduced that, let's go ahead and write down its definition. This is what we'll be working on the rest of the hour and next time as well. So I'm going to define the apsidal angle. Apsidal angle. So we've got everything here. By the way, for this omega sub phi, we could, what was that? L over M R naught squared. Okay. So absolute angle C is equal to omega sub phi times T sub R divided by 2. So this angular frequency times half of that radial period. That sweeps out this angle here. What would it be for the Kepler problem? Closed orbits, it would be equal to pi. So let's just put that in the notes for orientation. For Kepler orbits, I'll call them the Kepler orbits, C is equal to pi. Yeah, but this is the thing we're going to work with now. So I'm going to make a couple of versions of this. This is its definition. Very clear what's going on here. Imagine the hands of a clock going counterclockwise, and then there's a beat on the clock moving in and out. You're combining those motions, and this is what you get. I'll draw this orbit fatter. There we go. There's the orbit. Again, when it comes back to the minimum, it's not going to close the circle at all, right? It'll come back down here somewhere. Okay, let's see. So this is one version of this formula, and the fundamental one that you could use, but there are more useful versions of it that I'm going to give next. So let's just express this in terms of omega sub r. Okay, so in addition, we know that using omega sub r, T sub r is equal to 2 pi, we just formulate this as follows. So we got omega sub phi, and then T sub r over 2. T sub r, we've got 2 pi over omega sub r. Got another 2 there. So here's our absolute angle. Omega sub phi over omega sub r and pi. So this is the one we're going to use in a general formula. Do you have enough time for that? You know, I think I'm going to assign this as a homework. I'll get you guys started on it. It's a great problem. And I think I'll give you the final answer to that as well. So yeah, in fact, that'll be a good way to end. I'll just formulate the homework problem and get us started on it, and then we'll get some good applications once we're done with that. Okay, so let's see, homework. Show that C is equal to pi divided by root 3 plus r naught u double prime of r naught divided by u prime of r naught. Okay. So that's the absolute angle formula for nearly circular orbits. That's what we're going to do, and then we'll get a bunch of examples with that. You know, I think I'll do the example and then I'll get us started, since I've just written this down. So the example. U of r is equal to minus alpha over r. What else? Okay, of course. So what do we have for u prime is equal to alpha over r squared u double prime is equal to minus 2 alpha over r cubed. And our absolute angle is equal to pi divided by the root of 3 plus, so we have r u double prime negative 2 alpha over r cubed divided by u prime alpha over r squared r squared goes against r cubed, alpha and alpha, so it's just 3 minus 2 equals pi over root 1 is just equal to pi. I'll just write it down like that, boom. Equals pi, and what is that? That's the closed orbit with the Kepler problem. But they don't all have to be closed. The exam problem had one that's not closed, and you'll see the significance of that exam problem now when you do this. Okay, so this is really useful, and we have to prove it. So let's get started on the proof. So it's nearly circular orbits, and so for the proof, we have to know that m r naught squared omega sub phi is equal to L. And we also had, we saw earlier this hour, m r naught omega sub phi squared is equal to u prime r naught. And the third ingredient is u effective L squared over 2mr squared plus u of r. So what you do is the following. Remember, you're looking to put our generic picture here. Okay. And here that r sub 0. What you do is you find r0, right, such that u effective prime of r0 is equal to 0. And then you find your omega sub r equals root u effective double prime r0 divided by m. You barely read that, but you heard me say it. Okay? And then this definition here, which before I erased it was pi times omega sub r over omega sub phi, or omega sub phi over omega sub r. You can get all of these definitions because your omega sub phi is in terms of this, your omega sub r is in terms of this, and you just, one more hint. What you'll be doing is saying c is equal to pi over omega sub r divided by omega sub phi. Okay. You set it up like that, and you will end up with this thing right here. Okay, that's an excellent problem. And we'll be able to work with it next time we meet. So let's see. So in the meantime, just keep taking good notes and see you next time.